Dude, I have like bags.
No, I just left my bangs.
Wait, I was like,
I didn't like shoot everything. I just like,
So I wear that bag. No, but I wore like have
as much like
bags.
I didn't do anything last night. Why am I tired?
yes, but mine's just like crazy. How
yeah.
so mine is like that.
Yeah, it's like
it's
it actually really
that's what's crazy.
Okay.
I depends on like this cut.
Remember after
It's
normal?
like it depends on
That was not cool.
it's like if it's just a length, like if I had my haircut like that,
Yeah.
it would be horrible.
It's
like all thick and lumpy and everything.
Oh, you guys
It's
just
like
like
if I have layers,
Mm-hmm.
then I can just
Oh my God.
Yeah.
Those are my curling irons.
It's not when I was
Wait,
in
what?
public.
Yes, it's
Oh,
in
yeah.
Wait, what?
I look over.
I know it's back. Oh my
I
God.
can see it.
What are you talking about?
Oh, wait, I draw right now.
You
It's
were
curling my hair.
I like talking while I was curling my hair.
I didn't see that.
Or it's like fried because your hair off.
I have this natural way.
The burn was
Yeah.
making pancakes. And she burned my cake.
And
Yeah,
that's like to tell my hair.
It's good.
Not curly, but wavy.
Yeah.
That's before I was raised.
And I
I
dropped it on my
But
shoulder.
So you didn't get it.
So
yeah, I feel it's not that way.
But I like no. Picked it up so quickly that it
Stuck
was
my
barely
hair?
touched. But it still hurt. I burned myself. Got it.
And like it was a hot topic where she gets like her forehead.
What is the tie?
I had this teacher that did that once, this dance teacher. She came in and she had this big burn on her shoulder. We were like, what happened, Renee? So she was like, I dropped it. Like she was like, and she just like dropped it. I was like, and then all of a sudden I was like, what? I forgot to put my hair down and it's hot still, and it like burns my skin. Yeah, she dropped it.
Or like my
I
skin.
had my straightener was starting to fall, like but it like flipped. So I went to catch it by the handle, and instead of like I got it by the other thing, and I like put my hand right on the plate.
I literally,
But I had this, like,
I was literally like sleeping on my eyes, but I was like,
In the car.
that's true. I wasn't really sleepy, but I couldn't. I looked like that's
I feel the worst.
But cause like there was like one there was like one there was like it was like 2 hours and I was like
Stop.
yeah, just like
other one.
it's like
What?
oh I always have this like I got no
I'll be like,
I was
and
yeah.
this one's
I was telling her
You're like, okay.
she was really sweet. With my scoop back. She like almost got my nose.
Oh my
and
God.
grab a can without ice in it.
and I'll like catch myself.
So yeah, I heard.
Oh yeah. It was painful.
That's the only one home.
I always don't think like, okay, out of the microwave or something, and it's just don't think about it, so I go ahead and eat it right away, and I'm like,
Oh, I know. No, I did coffee. I was like, I'm too.
When did your burn?
Yeah, I have to have
Just
it.
like
It was like when I like,
and then you're like, oh,
6:30.
oh,
Yeah.
and I had to like
switch to
I got
okay,
it.
okay,
I know. It is.
Oh yeah, I thought
Yeah.
Always like
You have
burns your taste buds,
yeah.
but you can't
You don't
taste
get
it.
coffee cold at Starbucks.
Before I get to this, this graph, which, there's like a medium size I'm trying to get to.
I know. I'm excited because like everybody's saying it, like, and it's like,
there you go.
It should be the size.
no, but I have been saying it's good.
Thank you.
Did you send it? You would
They're like, ew.
Well, we'll just do this one, right? The best of my own personal life.
That's it. Yeah. I know. I was like,
Okay. We made a comment in the last period that now that my 10th digit of my age has increased by 1, I'm going to be more irritable, crotchety, and everything else. So, yes, and I would probably have less patience and all of those things, and my hearing will probably be worse, so, you guys have to be extra quiet. Yeah. So just keep that in mind as the school year goes on here. Be gentle, right? Now that I'm, an old person.
He's very frail.
Yeah, be considerate of my old age, please.
Oh my goodness. I was like dying over.
Okay, let's review for a second. Before we get into the solubility graphs, let's review. When we're making solutions, we normally have something that we dissolve into something else. The something that's being dropped into the something else is in general referred to as the solute. And the stuff that it's being dissolved into is the solvent. A common solvent is water. Actually, water's, the book refers to it as the universal solvent. It's a common solvent, it dissolves lots of things. Now, how much you dissolve determines how concentrated your solution is. Put a couple grains of salt in, the water's not that salty. Put more salt in, the water's more salty. How do you measure concentration? With molarity. It's moles of solute per liter of solution. Moles of solute per liter of solution. If you make an expression like so, this is going to give you some molar measure of how concentrated your solution is. That's a capital M for molarity. There are what, 3 underlines is capital, right? Isn't that the proofreading technique?
Mm-hmm.
Yeah, 3 underlines, so capital M. Now remind me, when you have a salt crystal, for example, that's dropped into water, what is occurring to allow the salt to dissolve? Like when we say the salt disappears, the salt really doesn't disappear, but the salt crystal does get broken down into really, really tiny pieces. And what allows this chlorine particle to be broken down? How do you get the chlorine particle from here to there? How are you going to get it away from its sodium that it's attracted to? Kramer?
Water molecules attack sodium?
Yes. So, if the water molecules attack, and the chlorine is negatively charged, so the positive portion of your water, which is the hydrogen, is going to orient itself around the chlorine. You get enough water attacking it, and it's going to be the chlorine ion, will be more attracted to the water than it will be its sodium next to it. At that point, you have a solution. So I'm being careful in drawing my H's bordering my chlorine. Because the H's, the slightly positive portion of the water molecule, are going to be attracted to the chlorine. It's the polarity of the water that allows it to dissolve the chlorine. We actually might do an experiment this week, a demonstration with water and isopropyl alcohol to see which dissolves salt better. Erica actually brought that idea up to me because that was something that she did when she was in high school chemistry, or at least saw done, and we could run that experiment and see which, like, if I asked you right now, which do you think would dissolve the salt better, water or isopropyl alcohol? How many people would be on the water side? And the isopropyl alcohol side? A couple more? Well, we'll see. Well, maybe we'll run that experiment, because it's, isopropyl alcohol is just like rubbing alcohol, so that's readily available for cheap. And
What's
water
the
is.
structure though?
That's a good question, right? I guess that's isopropyl alcohol. I believe.
Perfect. I love it. I love it.
Yeah, ask and you shall receive, right?
You broke it.
Yeah, I broke it, but that's,
That's perfect.
thank you. So yeah, this is the structure of isopropyl notice there's a lot of carbon-hydrogen bonds. Those are not very, well, there's a lot of carbon-hydrogen bonds, and there's one oxygen-hydrogen bond. Now, if you look at all the bonds, oh gosh,
Do you want me to do it?
I might
Or
have
you
done
want
that.
it?
Old people in
Hey,
technology.
yeah, old. We have to slow down and focus, right? Now, when you look at the electronegativity of the bonds, you have, if you look at the periodic table here, we know hydrogen's way the heck over there, way away from fluorine. But when you consider oxygen, which is right next to fluorine, then nitrogen, then carbon, then boron, for that matter, but the carbon-hydrogen bonds are less different in electronegativity than the oxygen-hydrogen bond. So over here you have this strong pole over here that creates a polar molecule. So over here you have this slightly positive side of the molecule, and over here a slightly negative side of the molecule. So there is some polarity, which would allow it to attack the salt. But yeah, what does this come out to be? C4, H, 1, 2, H9OH. I believe that's isopropyl alcohol. I believe. I could be wrong, but I think I nailed it. At any rate, that's the. I'm thinking it's wrong.
Double checking you, yeah. 'cause
Yeah, double check it's C4. I'm
It
almost.
doesn't look right to me.
I'm thinking it should be C3. I think I have too many carbons. But anyhow, that'll be our experiment. That's a good question, Marty. Like, what is the structure? At the very least, that's a simpler molecule. So does the simpler, yeah?
The C3H8O.
Oh, pooper. C3. Oh, right. This is isopropyl alcohol. There it is. That's it. The alcohol is on the middle carbon, because iso is a word in organic molecules. Those are like your proteins, fats, carbohydrates, lipids. This is a carbohydrate here. The iso molecules are balanced on both sides, so they're like symmetrical molecules. That's what the iso means. So to make it symmetrical, propyl means 3 carbons. To make the alcohol, this is the alcohol group, symmetric, about 3 carbons has to be in the middle one. Anyways, long story short, what do we say? C3H8O. So polar molecule. This guy's polar. So he will dissolve. But he's this slightly more complicated C3H8O versus the H2O. And you would think isopropyl alcohol, like just with the smell of it, with the consistency of it, with the nature of it, it might dissolve lots of things, because if it dissolves like nail polish, maybe it dissolves salt better. That would be something interesting to see. Now, another thing, just to remind ourselves, when we start dissolving substances in our water, like if we've got our water molecules, but then mixed in among the water molecules we have these little salt crystals. Remember, it's harder to boil the water, because when the water's trying to boil away, it's going to be running into those salt crystals on occasion. So remember that whenever we boil something, the boiling point elevates from the presence of foreign objects. When we try to freeze something, it's going to be harder for those water molecules to freeze as well, and we have freezing point depression as a result of particles being dissolved. So the boiling point will elevate, it will be harder to boil, and the freezing point will depress, it will be harder to freeze as well. You're gonna have to get it colder to freeze. Okay, now, review aside, let's get back to the picture that I pulled up here. And then there's a copy of this graph in the book, if you were curious. Just to have for reference, page 298, this graph that we have pulled up here. Now, what is this graph? This graph says grams of solute per 100 grams of water. So this is telling you how many grams of salt, how many grams of potassium nitrate, how many grams of sodium nitrate you can dissolve per 100 grams of water. So, look at this graph here for sodium nitrate, NaNO3. At 0 degrees Celsius, you can only dissolve 72 grams, but at 60 degrees Celsius, you can dissolve 125 grams. Now think about that for a second. Why would you be able to dissolve more of something whenever it's hotter? Why would temperature affect the solubility? What does temperature affect? Movement. And why would freer moving particles cause the solubility to increase?
Can attack the other ones.
They can attack more readily. Perfect. Okay. Now, you notice not everything works that way. NH3 is a gas, as a general rule, increases in temperature will increase solubility of solids and liquids, but will decrease solubility of gases. That's a general rule. When you increase temperature, it will be easier to dissolve the solids and liquids. You'll have more water to attack. But with gases, as the water is moving more vigorously, it'll force the bubbles out. You've all experienced this, I am sure. When you take the carbonated liquid and you keep it cold, it takes longer to become flat. When you take the carbonated liquid and you set it out on the counter and the temperature goes up, it flattens out really quick. Why is that? Because as the temperature goes up, the solubility of your gas goes down. Heat up your soda and the bubbles will evacuate. The bubbles will leave. However, heat up your salt water and you can dissolve more salt. When you're dissolving a solid, the solubility is going to increase with temperature. Now, let's try to look at the information on this table. Let's try to grab some bits of information off the table, and then let's try to express these solutions rather than grams of solute per 100 grams of water in terms of molarity. So I'm going to pick that one right there. Look at that NH4Cl. It goes right through the crosshairs. So it looks like at 50 degrees Celsius, NH4Cl will dissolve 50 grams in 100 grams of water. Now, what we're going to try to do is express this concentration in terms of molarity. We can get 50 grams of NH4Cl in 100 grams of water. Express the concentration in terms of molarity. Let me write out what molarity is. Molarity is moles of solute per liters of solution. So, how could we figure out moles of solute? First off, what is our solute in this problem? The solute is NH4Cl. We're dropping that into our water. So that's like our salt part, the NH4Cl. Now, we know we can dissolve 50 grams of it. How are we going to get from grams to moles? How do we get from grams to moles? Periodic table. So let's go to our periodic table. The N has a mass of 14. H has a mass of 1. And chlorine has a mass of 35.5. So put those together. You have 1 nitrogen, 4 hydrogens, and 1 chlorine. You can add that together, and that's going to give you 53.5 grams per mole. Now, we can dissolve 50 grams, that's what our chart told us. So, how am I going to take this to moles? Start with the 50 grams, and then do the conversion, 53.5 grams for every mole. That'll get you from grams into moles. We almost have a mole, right? If a mole is 53.5, we have 50 grams, it's almost a mole. But in specific, if we ran the numbers on that, then we'd have the value we need. So I'm going to grab a calculator. Take 50.5, or 50 rather, and divide it by 53.5. And that comes out to 0.93 moles. So we have 0.93 moles. Specifically, I'll write it out here, of NH4Cl. That's our solute, and that's the number of moles of solute. Now we need liters of solution. But all we were told was we dissolved it in 100 grams of water. Does anybody remember the little fact about water way back in the day? We said 1 gram of water occupies a certain volume. Does anybody remember? 1 centimeter cubed, which is 1 milliliter. If you happen to have forgotten this, make a box 1 centimeter, or actually, yeah, make a box 1 centimeter in every direction. Make a centimeter cubed. 2 things. That's a milliliter of volume. If you filled it with water, it would weigh a gram. So those are your 2 facts about water. One is, fill a cubic centimeter, you'll get a gram. 2 is, any cubic centimeter is a milliliter. Those are the same units. So think about this. 100 grams would be 100 milliliters of water. Because every gram is a milliliter in water. Water is unique in that its density is 1 gram per milliliter. Well, how could you take 100 milliliters to liters? Do a conversion. There's 1,000 milliliters in 1 liter. So 100 grams makes 0.1 liters. It's a tenth. 1,000 milliliters would be a full liter, so we have a tenth of a liter. So 0.1 liters of water. We do the division, and we come up with the molarity. So 0.93 divided by 0.1, and you'll get 9.3. So, at 50 degrees Celsius, if you're using ammonium chloride, the maximum concentration is 9.3 molar. Let me just be clear about this. If you wanted to, if this is 9.3 molar, you could dissolve less than 9.3 moles if you wanted, right? What if you just take a little bit and throw it in? Clearly, if 9.3 moles can dissolve, well then 8 moles could dissolve, or 7 moles. But you could not go above this number. What this line is showing is the maximum amount you could possibly dissolve. So if you tried to dissolve more, you're going to have crystals left at the bottom. Like you put too much Gatorade powder in the water, right? And now the Gatorade powder is just sediment at the bottom. Same idea. So you could always put too little Gatorade powder, and you'll just have watered down Gatorade. But when you put too much, that's when you start getting the sediment. This line is showing the maximum amount that can dissolve. And notice it's affected by temperature. These ones that are going downhill, gases. The ones that are going uphill, solids or liquids. That's the general rule when it comes to solubility. But for any value on there, I mean, we should be able to use any value on there and come up with a molarity. This is a good device. This graph is a good device to practice this. So let me give another example. Now just take a look at the picture. Okay, let's say at 30 degrees C, what is the maximum molarity of a let's do KCl, of a KCl solution in water. 30 degrees C. So come over here to the chart. You can see the line for KCl. Travel it back to 30 degrees, and it looks like at 30 degrees, we're right in between 30 and 40 grams of solute per 100 grams of water. So it looks like 35 grams. So from the graph tells us we can do 35 grams of solute per 100 grams of water. Now, if we want to take that to a molarity, we're going to have to talk in terms of moles of solute and liters of solution. So let's express moles solute over liters solution. We know we can put 35 grams of solute in. That doesn't tell us how many moles. But if we go to the periodic table can tell us how heavy a mole of KCl is. The potassium weighs 39.1 and the chlorine 35.5. So one particle of each, just add those numbers together.
74.5.
74.5 grams per mole. That's for your KCl. Thank you.
Yeah.
So, if we have 35 grams of solute, we know, I'll put this over here, 35 grams of KCl, but we know that there are 74.5 grams in 1 mole. Looks like about half a mole. 0.47 moles. Which means, for this solution, at most, we can dissolve 0.47 moles. We could dissolve less, but at most 0.47 moles. When it comes to liters of solution, we use the same trick we used before. 100 grams of water is 100 milliliters of water, which is 1/10 of a liter. The charts are all calibrated the same way. It's per 100 grams of water, so you'll get used to that trick. 100 grams is 100 milliliters, 100 milliliters is 0.1 liters. Do the division, and you get 4.7 molar. Maximum concentration of KCl, 4.7 molar. You go up to 4.8, you're going to have sediment at the bottom. You go 4.6, you could have added more and still had your solution dissolve at 30 degrees Celsius. Change the temperature, you change the solubility. Because the faster the particles are moving, the more readily the water can attack the solids or the liquids. The faster the particles are moving, it forces out the gas bubbles. That's one way to think about it. You got these vigorous moving water particles, they're going to be bombarding against those gas particles, and those gas particles are going to be shooting out into the atmosphere. When it gets too hot, actually, when it gets too hot, what is it? Animal life in water slows down. Because hot water can't hold as much oxygen as Earth's temperatures rise and water temperatures rise, there's less oxygen dissolved in the water, it's harder for animal life to survive. But cold water dissolves more oxygen, easier.